Okay, so we're going to look at how we can calculate the volume of a solid of revolution when we re rotate one of these regions about one of four possible lines. So it could be x equals 0, x equals 1, y equals 0, or y equals 1. And for that, we're going to use the disk washer method, where we're going to have the large radius represented as, like, the distance from the axis of revolution to the edge of the solid, and little r of x be the small radius, and that'll be like the hole. This is going to be in terms of x when we have a horizontal axis of revolution, and we're going to integrate with respect to y when we have a vertical axis of revolution. Now, I'm only going to focus really on setting up the integral and not really spend time on doing the actual like calculation after we set it up, because that's really not the that's really not the lesson here. That should actually be the easy part, and that way I don't spend as much time. Okay, so let's look at the first one. So we're going to rotate R1, this pink region, about the line x equals 0. So we're going to rotate it about the y-axis essentially. So let's draw like a little sketch of what that could be, what that can look like. So R1 is bounded by the line y equals x. And on top we have the line y equals 1. That'll be at 1, 1. And so we want to revolve this, about this axis. So we're going to integrate with respect to y in this case, because it's a vertical axis of revolution. So essentially the way I look at this is, starting at the axis of revolution, draw a perpendicular line to the outer edge of the area that you're going to rotate. So this pink line would be my large radius, and since it's in terms of y, it'll be large r of y. So it's always going to be from here to there. So you can vary, but it'll represent the distance from here to there. Now, this one is pretty straightforward because you already have the equation. You just have to make sure we write it in terms of y. So our equation is just going to be r of y is equal to y. Now, the inner radius, there actually isn't one, or it would just be 0, because there's actually not a hole. If you were to rotate this, you get like a cone, like a solid cone with no hole inside. It would be completely filled in. So your volume would essentially be equal to pi times the integral, and we're going to go in terms of y from here to here, so 0 to 1, r of y squared, and that's going to give us y squared dy. And if you were to integrate that properly, you would end up with pi over 3 as your answer. For the next one, we're going to this time rotate R1 about the line x equals 1. So we're going to rotate about this line that'll be drawn through that. Let's make a sketch of what that would look like. So we have that's not perfect for that. It's supposed to be our y-axis. That's our x-axis. R1, something like this. The line y equals 1. Our axis of revolution would be this line, x equals 1. Rotate this about that. And that's at 1, 1. Now again, since we have a vertical axis of revolution, we're going to have our integral written in terms of y. So we're going to need to figure out an equation for the outer radius. So again, going from like the axis of revolution, I would just draw a straight line to the edge of the area or the solid that we generated. So it would be like this pink line. That would be my r of y, my large R. Now this one actually is very simple because it's always going to be equal to 1. It's always from here to here. So large R of y is simply 1. Now, if we were just to rotate that about this line, x equals 1, you would get a cylinder, but you would get a solid cylinder. Now we need to have a cylinder where it's, it has like a triangular hole, like a cone removed out of it. So we need to figure out the equation of this length. That would be your little r of y, and that would be small r of y. Now, common mistake is to think that this length is equal to the equation of this line. This line again is y equals x. But this line, or that equation for that line, will actually give you this green segment, the length of this green segment from there to there. It would always give you the length of these green segments. But we want the lengths of the blue segments, or the distance from here to here. However, we can use this to find the small radius. So if we think about it, so each of these line segments are basically just the pink segment minus the green segment. If you have the pink segment minus that green segment, you're going to get the blue segment. The pink line or the pink segment is always equal to 1. The green line is generated by this equation. So you'll have 1 minus y. That'll give you a little r. So r of y will just be again 1 minus y. Because y again is this length here. Now you can set up your integral as the volume being pi times the integral from, again, we're going to go from 0 to 1. The outer radius, large R of y, is 1. So we're going to have large R of y squared, which will just be 1 squared or 1, minus small r of y squared. So 1 minus y squared like that. So let's just kind of expand that and simplify it. So we'll get 1 minus 1 minus y, so minus 2y plus y squared dy. Those ones will cancel. Minus a negative 2y, so it'll be positive 2y minus a y squared dy. And if you were to integrate this properly, you would end up with 2/3 pi as your final answer. Okay, now let's look at the third one. We're going to have R2, so the screen region rotated about the line y equals 0, so about the x-axis essentially. Let's draw a little sketch of what that would look like. We have this here. This will be the line x equals 1. we want to rotate about this axis. This is our axis of rotation. Okay, so let's make that y. That's y equals x. And then we actually need this line too. That'll be y equals x squared. Okay, so we're going to integrate with respect to x since our axis of revolution is horizontal. We'll write our radii in terms of x. So again, let's start at the axis of revolution. And from here, we draw a line segment out to the edge of the area. This will be our radius, our big radius. That'll be large R. So this is pretty simple because we already have an equation for that line. So large R of x is simply just x. Now, what we need to do is then find the equation for the distance from here to here, because we need to basically subtract this area, or like the solid that'll be generated here to rotate this. So it'd be like a weird like cone with the like inverted cone like taken out of it, I guess. So this will be our small radius from here to here again. And this one, we already have an equation for this line. This is just the parabola where y equals x squared, so little r of x is just equal to x squared. So now we can set up our volume as the integral from 0 to 1, big R of x squared, so x squared, minus little r of x squared, so it's x squared squared. Not really much simplifying to do. It'll just be like x squared minus x to the 4th dx. And if you were to integrate this properly, you would end up with 2 pi over 15, or 2/15 pi.